Hey everyone, I am Boray. I worked at o1Labs as exploration engineer. I also study mathematics at Boğaziçi University. Today I will be talking about building stateful zkApps using o1.js and Mina. So first I will be talking about o1.js and Mina Protocol. Let's start. So Mina is a succinct blockchain. In Mina, everything is a proof. Everything is snarked. Every transaction is snarked. Every block is snarked. Every consensus rule is snarked. Every computation by every user is also snarked. Also, every snark is also snarked recursively. So at the end, we have a snark proof that we can verify whole blockchain state. And also not the current block, but all blocks that happened, that is in the blockchain. We can verify all of them with only one snark proof. It's decentralized. The sequencing, proving, and end user usage is decentralized thanks to snarks. So we don't need like services like Infura or Alchemy to interact with the blockchain. We have something called light nodes, so users can have a succinct proof of the whole blockchain and some necessary data to verify and prove their accounts. And basically, users can interact with a very succinct data and without an intermediary. And it also scales well thanks to snarks. It allows privacy thanks to snarks. We can have smart contracts with private methods, methods that have private inputs. Also, we can compose proofs, which we do in the blockchain level, but we can also do that in application level. We can build applications that can verify and also produce recursive proofs. So the proof system that enables this is Kimchi and Pickles. Kimchi is a Plonkish proof system that supports a rich set of custom gates, Poseidon, main check, Zor, rotation, foreign field, and it supports lookups. It doesn't have a trash setup. Also, we have some cool features coming soon, like KZG backend, folding, chunking, and more. And the Pickles is the recursion layer of our proof system, and it has been mainnet. It has been live since the mainnet. So it's not only helping the Mina blockchain to be succinct, but it also helps us to build recursive applications. So o1.js, it's a zero-knowledge SDK that we develop as o1Labs. It's written in TypeScript. It's easily accessible by Web2 developers. Also, all Web2 tooling is easy to integrate with o1.js because it's TypeScript. And it has a rich library of primitives. It supports custom gates, and that comes from the proof system. We also have optimized gadgets for signature shims and hash functions and bitwise operations. Yeah, so o1.js provides two classes to build zkApps. The first one is ZK program, and I will go over that a bit. So this is basically a circuit in Circom. It's a circuit. It doesn't have a state. It's pure, and it has methods. In this example, this is a recursive proof. So we have a base case and an inductive case. These are methods of the ZK program. The public output of these methods is fields. So the base case returns a field, a zero field. Then the inductive case, the recursive method, takes this proof, then verifies it, then adds the public output of this proof, adds one to this public output, then returns it. And then you can take this proof and pass this method as an argument. Then you can do it recursively. And at the end, you will have a proof that you can verify, and you can verify this whole computation. Smart contract is another class that o1.js provides. Smart contract is like ZK program, but it enables us to build zkApps that interacts with Mina blockchain. So here we have states. They are indicated by the state decorator. We can have 8 states in Mina blockchain, so we can have 8 state fields in a smart contract. We have an init function that helps us to add custom logic to deployments. Then we have methods. Methods are provable. They are basically every method is a ZK program itself, and they can have private inputs. And we can do computations on them, and we can interact with the states. In this example, we fetch the state, then constrain it to make sure that the state is same as the on-chain state. Then we add 2 to the current state, then we update state. Then this will be an account update. Then it will be put it into a transaction, and we will prove it again. So zkApps. So in order to build a zkApp, first we need to build a smart contract, as shown is in this example. Then we will need to compile it. In this context, compilation is a bit different than programming languages. We don't compile to a bytecode or machine code, but what we do is it generates provers and a verification key. And we take that verification key and deploy an zkApp account with that. This is actually an atomic operation. You just deploy an zkApp account. That's the verification key is set automatically. Then after that, when it's verified and when it's put into a block, we can prove a computation locally with the smart contract. Then we generate a proof and we send it to the network, Mina network, with a transaction. Then Mina verifies the computation with the proof and the verification key. And if that's also valid, the network applies the account update and updates related state fields. So stateful zkApps, the title of this talk is, so zero-knowledge circuits like ZK programs doesn't have state, they are pure. But in order to build smart contracts like Ethereum, like DeFi applications, DEXs, NFTs, and all that stuff, we need states. And Mina enables to hold 8 state fields, 8 fields in state. But there are some problems. So first, it's not enough to hold a mapping. And then, since everything is proved, we have some problems that the other blockchains doesn't have, because in Mina, everything is approved. Some others don't prove everything, but we do. So we do have these problems, but we have solutions too. So let's say we have a state field. We have a simple zkApp, and we want to update a state field. How do we do that? So basically, we can do that as in the previous example. But in a zkApp, there will be more than one users. So we need to update state fields concurrently. So in this example, Bob and Alice wants to comment the state field by 2. And they run this same computation in their local machines. Then they prove this computation, and they send this to Mina network as a proof. And this transaction holds this data, and it has a precondition. So networks has to check the previous value of this field. and the value that the user wants to update. So they have the same precondition and updates. That will be a problem. Before the solution, the problem is, so when the network applies this transaction, the state field will be 3. Then it will try to apply the second transaction, and the precondition will not be met because it's not 1, but it's 3. So the second transaction will fail. And what this means is the throughput is limited to only 1 state update per block, which is not good. So how do we solve it? Actions and reducers. So maybe some of you are familiar with this concept from Mina or Redux or somewhere else. In Mina, they are similar to all implementation of action and reducers. So in Mina, actions are events, but they are sequenced. Events, you can think like the events in Ethereum. They are commutative when they are not in a block, when they are emitted, but when they are put into a block by a block producer, they are sequenced. So after the block production, there is no extractable value from the ordering. They are stored in Mina archive nodes, so there is no extra additional dependency to an additional data storage layer. And a commitment to action is held in zkApps state, so archive nodes cannot tamper with actions. And with reducers, actions enables handling concurrent state updates. And these updates are lagging. They are not applied simultaneously, but they need to be reduced in order to make into the on-chain state. So I will go over an example of setting up a simple reducer. Then I will set up an more functional one. So we import the reducer, then we set the action type, which we will dispatch. Then we can dispatch an action like this. It will be in a method, and user will interact with them. Users will dispatch actions. Then when reducing, we have a couple of variables like state type. This is the type of the state which we will store on chain. Then we have actions which we will normally fetch from archive nodes. Then we have the initial value which we will fetch from on-chain state. Then we reduce it. So we pass action, state type, and a function to reduce to the reducer and the initial value. Reducer will use this function and the other variables to reduce actions, then return the new state. Then we can update the on-chain states with this new state. So let's go over a more practical example. So this is the previous example where we had a problem of throughput. In this example, Bob and Alice want to increment by 1, but they don't dispatch preconditions or updates. They increment an increment object. So they do that, and they both send their transactions to Mina network, and they are both valid because they don't update any state fields. So there is no concurrence there. But when their transactions are verified and put it into a block, the state field is not incremented yet. So we need to set up the reducer for this example. So we have this increment object which we will dispatch. And we have maybe increment class to have more flexibility, because maybe users won't dispatch increments, but they will just increment actions, or we can have more. We can do more stuff there, but I will keep it simple. The action type is maybe increments. Here we have a counter. That will be state field that we will be updating. We have the action state as a state field. It's a commitment to the actions that is stored in archive nodes. Then we have a method, and in that method we dispatch an increment action. So users can run this method and dispatch an action. So when reducing, we fetch actions from archive nodes. This is the state field. And we have a different reducing function. Here we have provable if, which is the provable equivalent of JavaScript if. It's same as that. And we pass the initial value, which is the on-chain state field. Then we reduce it, and we update the counter with the value that reducer returns. So now the increments are happened, and now the state is updated, and there is no concurrency here. So yeah, updating a state fields is solved, but in order to make better zkApps and let's say non-trivial ones like more conventional ones, we need mappings. And storing and updating a mapping is a bit hard in provable fashion. It's not that easy like Ethereum, but we have a solution. So we need to store the mapping provably. So the thing we need is Merkle trees. We have a sparse Merkle tree here. So some of the leaves are null. We store key pairs as leaves. Then we have a root which we can store in an on-chain state field. So we can store a mapping like this, but there is a problem. So let's say you want to update key pair 1. So this will be changed, and since we hashed these two, the upper node will change and the root will change. And it works for now for only one update, but if you want to process two actions at the same time, which will it will happen in production, it won't work. So it was supposed to come when I press, but anyways. So Alice and Bobs wants to update two different key pairs here. And what they do is they update this and they compute the root and the proof, and they send it to network. And Bob does the same, but for the key pair 2. But what happens is, when the network processes these transactions, the first will be valid because this is the precondition. The first root, it's an on-chain state field. It will update to the root asterisk. But then, when it's processing the Bob's transaction, the precondition will be root, and the new value will be root double asterisk. But the actual state will be root asterisk because it's already processed. So Bob's transaction will fail, and this also creates a throughput problem where only one update can be done per block, which is quite bad. So the solutions of Chain State API, it's quite new. It's released in May, thanks to Gregor. With off-chain state API, state changes are emitted as actions. Merkle tree operations are abstracted, so we don't deal with Merkle proofs and roots. But off-chain state API handles for us. And recall actions are stored in archive nodes, so we don't have a data availability issue, let's say, because they are stored by Mina archive nodes. And it provides two primitives, off-chain map, which, as the name tells, which enables us to have maps, off-chain maps, and the other is off-chain fields, which enables us to store any type of data that can be derived from fields, like UN64 or anything else. So this is how we set up the off-chain state. It's quite easy. It's in the experimental namespace right now. We import it, then we define off-chain state. We have a player map here from public keys to Uniswap, then a total score with type of Uniswap. Then we have a state proof here. We will use this later to settle the state because like in action and reducer pattern, we need to reduce the actions we dispatched. In off-chain state, we call it settlement. So we need to settle those changes, and it's a bit different from the reducer, and it will generate a state proof, and we will settle with that. And here we have a on-chain state field to keep a commitment to the off-chain state. So when updating it, we have two methods for each, for field and map. We can either update it, we can give a precondition, so it can check if it's the actual value on the blockchain and update it to a new value, or it can overwrite the existing value with the value we gave. So yeah, like I said, we need to settle the proof, settle the state, off-chain state. So off-chain state uses a ZK program instead of a reducer. It's a reducer actually, but it's a bit different, and I will talk about this later. It gives a method, create settlement proof. We create a proof with that, then we take that proof and give it to the settle method that we added to our contract. And what this method does is it verifies the proof, then it updates the on-chain state fields, and after that, the all state changes happened in actions are now on-chain. So this is cool, but how this API works. So unlike the traditional actions, traditional reducers, here there is a ZK program reduces actions and applies state changes to the Merkle map, Merkle tree. But the ZK program has a circuit size limit like all other circuits. And we may have a problem there because if a certain amount of actions are dispatched that could overflow the circuit size, what could happen is ZK program wouldn't be able to settle actions and apply all actions. Then basically the off-chain state will deadlock, and that's not something we want. So what we do is we process them in batches. These batches are number of actions, it's a fixed number. And we process them recursively. So let's say we take n actions, we apply the state changes, then it generates a proof. Then we take that proof and we take new actions, n number of actions. Then that method generates another proof, and we are doing that recursively. And finally, it generates a settlement proof. Then we settle it, and we settle off-chain states. Also, settlement is in a topic itself because it's a lagging state like actions and reducers. So we need to provide some nice UX. So settlements is creating a settlement proof with a ZK program and updating the off-chain state commitment on-chain. And they need to be settled regularly enough to ensure a smooth UX, because if not, then like if the frequency is too low, then users will feel that zkApps is not responsive because they wouldn't see their state changes fast enough. And if the settler does it in a like high frequency, then basically she will pay a high transaction fee because he or she has to do it like regularly. So there's a balance there. And also there is no permission to settle. anyone can settle. Users can do it, developers can do it, a third-party service can do it. And also various economic mechanisms can be designed for that. For example, a developer, zkApps developer can tax users with like small amounts, then rewards the person who creates the proof and settles with that tax revenue. There's also other creative mechanisms can be designed there, so there's lots of room for creativity. Thanks. If you want to check out the example, it's here. It's in the o1.js repo, and we will be releasing an example using off-chain state soon. I hope after MinaCon, it will be released on Discord. Thanks again.
All right, thank you, Boray. It was a great intro to Mina and Owen for the ones that didn't know about this, and stateful zkApps. Do we have any questions, first of all? If you have a second, maybe to answer them. Guys, any questions? Yes. I don't have a very long mic, so.
Okay, I can speak.
Yes.
Where does the number 8 come from for the state?
Where does the number 8 come from? For?
It's a good question. I think it's a better question for Brian.
Hello. Where does it come from? Well, it was chosen because it definitely was small enough to have Mina work. But the question is, how big can we grow it and still keep the network stable and healthy? And the answer is much bigger. And the third question is, well, are we going to do that? And the answer is, if the MIP says yes, then yes. How's that?
Yes. I'm not sure if I can reach you.
I can't bring the mic over here.
Oh, okay. I always have a basic question. The data structure, including the online and online data structures interaction. Consider that every node has an offline storage organized in a Merkle tree. So the root hash of the Merkle tree, how to verify on the whole network how to verify the root hash of the private Merkle tree on chain.
So you mean every user and client has its off-chain state, and how to apply those changes?
Make sure that to verify, how to make sure that every root hash of every private storage is correct. It's correctly computed, because it's part of micro-research topic. So I wonder that because the Merkle tree proves the value integrity by the root hash, so how to make sure that the root hash is correct after storage, private storage.
So I can maybe explain this better over this example. So the question is, the user creates a settlement proof that's client side. Then how this state change is applied on network, right? Is this the question?
You mean that the root hash contained in the settlement proof, right?
Yeah.
The hash of the Merkle root, that hash containing the settlement proof.
Yeah. So when creating a settlement proof, the data we access is on archive nodes, so anyone in the network can access it, and it's public. Actions are public, and zkApps hold a commitment to that actions. So archive nodes cannot tamper with those actions. Also, if you fetch them, you can verify client side. Then when creating a settlement proof, you do the same. You fetch actions, you verify them, then you run the ZK program, and it generates a proof, a single proof. And when you verify that, or any participant in the network can verify that, when it's verified, that it proves that the necessary state changes are applied for the dispatch actions. So it also has a it also updates the proofs as the root hash as well, but it abstracts them. You don't deal with them. Then when settling, the settle method does that. It checks the previous root hash, then verifies the proof, then updates the proof, and that's a proof as well because it's a transaction. Then it's broadcasted in the network, and with that transaction proof, block producers verify that proof. Then when they are getting into a block, they are also verified and proved again. So so there is no way to tamper with off-chain state here. Yes, Mate.
So when you restate for your off-chain state API, how do you extract the linkers from the events? What kind of query do you make to the archive node? What kind of data do you request? Do you reconstruct the whole tree locally so that you can do the business, or what is the life cycle like?
Yeah, so we use fetch actions. Then now it reconstructs the Merkle tree on fly every time. So it's I think it will be optimized. Yeah.
So when you write data, is it events or actions?
It's actions.
And which account does the action statement go to? I mean, if you have a reducer, right?
Mm-hmm.
You have one action state.
Yep.
And then you're writing data.
Yep.
So you're writing actions again.
So
Different account, or how does it work?
So anyone can dispatch an actions. That's non-permissioned. But when settling, the settlement method does that for you. So it fetches actions, then creates proof. You don't deal with that stuff. On all Merkle tree reconstructions, you don't deal with that. Yeah. Any questions? Thank you.
Thank you, Boray. And yeah, thanks everyone. That's all for today regarding talks. And yeah, I guess now we can move on to a bit of drinks and food. Thanks for coming.